In today's video, here is a nice problem regarding arithmetic and number theory. Here is the following setup. Find all n, k as a non-negative integer, satisfy this following equation. We have n plus number 1 all to the k minus number 1 equals n cubed. Okay. In fact, this is very nice and interesting problem to work on. So you guys, you can give the hand to this problem prior getting to the solution. Go ahead, pause this video when you come back to see the full solution. Okay. By the way, don't forget to hit the subscribe button and support the channel. So let's jump into this one to see what's given us. Okay. So in order to solve this equation, we are going to determine the parity of n and k. Okay. Before we know the parity of k, we must know the parity of n first. Okay. Before we proceed with the parity, we must check the obvious cases first. So if n equals 0, so I get here 0, 1 to the k minus 1, which is 0, equals 0 here. So which means this one automatically is given as 1 to the k minus 1 equals 0. So this one is telling us 1 to the k equals 1. This one is for all k as a non-positive integers. Okay, we'll get the first obvious solution. I get n equals 0 with k. K can be anything, because since it's located at the exponent here, it can be anything. This is true for all k. Let's move on to the next value. N equals 1. I'm simply doing the same thing, replacing this one into this one here. I get 1 plus 1, which is 2 to the k, minus number 1 equals 1. Taking 1 to the right, I get 2 to the k, which equals t. This one, which equals 2. This one is starting as k equals 1. So we have the second solution. I get n equals 1 and k equals 1. Let's check the next value. N equals 2. N equals 2. I will have 2 plus 1, which is 3 to the k, minus 1 equals 2 cubed, which is 8. So moving over minus 1 to the right, I get 3 to the k, which equals 9, is the same as 3 squared. This one is telling us k equals 2. So we have another third solution. N equals 2, k equals 2. Okay, we are going to stop with these obvious values. We are going to move on to the general case. Okay, before we move on to the general case, we must know the parity of n. Let's work out a little bit with this one. Let's move over minus 1 to the right of this equation. So I get here n plus 1 all to the k equals n cubed plus number 1. Since we have 3 here, since we have 3 in exponent here, I'm going to factor out this one on the form of a product. I get n plus 1 factor n square minus n plus number 1. Okay, so since I get n plus number 1, I'm going to cancel out n plus number 1 from both sides. So I get here n plus 1 all to the k minus 1, which equals n square minus n plus number 1. Also, I'm going to take n as a common factor here. So I get n is multiplied by n minus 1 plus number 1. Okay, for all n is super equal to 2, we get this one. We know this one is even. Okay, which means the whole thing is odd. Since the right hand side of this equation is odd, which means the left hand side of this equation must be odd as well. Since we have since these two terms separated by number 1, so which means n must be even. N is even. Now we have determined the parity of n for all n is super equal to 2. Now let's check the parity of k. Okay, so we are going to assume k is odd, and at some points we are going to extract the contradiction. Okay, so since k is odd at this point, so now we are allowed to factor out this one on the form of the product. So we're assuming this one as x to the k minus 1. Okay, is going to be factorized on this form: x minus 1 factor x to the k minus 1 plus x to the k minus 2 and plus x to the k minus 3, and all the way down until you get number 1. Okay, so I'm going to write this one on this form. So now by continuing solving this one, I get here n plus 1 minus 1 factor n plus number 1 all to the k minus 1 plus n plus 1 all to the k minus 2. This one keeps going all the way down until you get number 1 at the end. Okay, so this the whole thing equals n cubed. So we get number 1 cancelled out, and also I'm going to divide both sides by n. So I get here n plus number 1 all to the k minus 1 plus n plus number 1 all to the k minus 2, and plus all the way down until you get n plus number 1 all to the 0, which is 1, okay? Which equals n cubed. The next thing up, I'm going to reduce both sides of this equation to the mod n. So this one is a congruent to 0 mod n. Okay? So get 0, this one is 0, this one is 0, and all the way down, this one is 0. I will be left with number 1, 1 to the k minus number 1, which is 1, plus 1, plus 1, and all the way down until you get number 1. This one is a congruent to 0 mod n. So how many of the number 1 that I have here? So this one is k times, because we get k minus number 1 times plus this 0. This is included, which means I have k times here. K times of, so which means this one, you'll have this one, k is a congruent to 0 mod n. So according to the divisibility statement, we get n divides k. It's equivalent. K equals m is multiplied by n. So we already know k was odd by this assumption that I have here, but n was even. It's clearly it's impossible. It's a contradiction, because always when we have even here, which means this result must be even, okay? Which is clearly it's a contradiction, which means k cannot be odd, which means k must be even. K must be even. So we have proven k is a even. Now let's get rid of this one and move on to the next step. Now again we are going to do this one by the way of contradiction. So by the way of contradiction, suppose for all n is strictly superior than 2, we have a solution for this equation, okay? So we are going to build a strong argument in order to prove we have no solution above this point, okay? We already know k is a even. Since n is a even, let's set k equals 2m. So I'm going to replace this fact into this one. So now I'm going to take this fact and insert it back into the original equation. So I get here the following. I get n plus number 1 all is raised to the 2m minus 1 equals n cubed. As we know, taking this minus 1 to the right, I get n plus number 1 all is raised to the 2m as an even exponent equals n cubed plus number 1, okay? So as we know, this one was on the form of the product n plus number 1 factor n square minus n plus number 1. Let's cancel out n plus number 1 from both sides. I will be left with n plus number 1 all is to the 2m minus number 1 equals n square minus n plus number 1. Let's transfer this one into the quinary square. So I get here n plus number 1 quinary square. So I'm going to recover that n square plus 2 times n, but I have minus n here, so we need to subtract minus 3n in order to fix this one. So I'm simply going to move over this n plus number 1 square to the left and factor out that. So I get n plus 1 square all is multiplied by n plus number 1 all is raised to the 2m minus 3 minus number 1, because I already moved this one to the left, which equals negative 3n, okay? Now since we get to this point, now we are going to make the comparison between the left hand side of this equation and the right hand side of this equation and check what's the status of this equation, okay? So as you know, this one is superior to 0. In particular, since we have n superior to 4, is strictly superior than 0, okay? Also, this one, for all m is superior to 2, this quinary is strictly superior than 0 as well. but the right hand side of the equation is strictly inferior than 0 because you have a negative here. Okay, so you might say, what about if m equals 1? If m equals 1 is not a contradiction because it's a family of the solution that we have previously found. If you replace m with the number 1, we get k equals 2, which we have it as a family of the solution here. Okay, so now we found a contradiction. So this is for all m is super equal to 4 and m is super equal to 2. It's impossible. Now, what we have contradicted, we have contradicted our assumption because we have chosen n is super equal to 4. We have a solution for this equation, but at the end we found a contradiction, which means the only solution that we have, only these 3 solutions. Okay, so by the way, don't forget to hit the subscribe button and support our channel, and thank you for watching. I will see you next video. Bye.